So how do you measure the rate of reaction? Well, basically, for this level, we'll study about 3 ways to measure rates of reaction. And it all depends on how the reaction is and what you're trying to mix. All right, so first of all, we will talk about using the volume of the gas produced. All right, so in this method, one of your products will be a gas, and you would collect and capture those gases and measure how much gas has been collected over a period of time. And so here I have a simple setup. It's actually 2 different separate setups that I just kind of meshed it to one because I didn't want to draw anymore. Here you have the conical flask with the reaction happening inside. You can see the little particles of different colored dots to represent particles or molecules, whatever. And when the reaction happens, the products, which one of them will be a gas, one of the products will be a gas, will kind of bump itself around the wall of the flask and then find its way all the way upwards to the delivery tube. The delivery tube, the rim of the flask is sealed not to allow any other gas, the gas to escape anywhere else. And the only, I say insert from the sealed rubber stopper is this delivery tube. So the gas will go up through the delivery tube all the way to the syringe, and when the gas arrives at the base of the syringe, it will push the plunger, which is this dark matter here, push the plunger outwards, all right? And so you will basically time this reaction in terms of minutes, seconds, or whatever, what have you, and then you will plot, collect it in a table based on fixed intervals. Another method is to invert or turn your measuring cylinder upside down, and the delivery tube will instead of going to the syringe, will go down into this little setup where you have a basin filled with water, and you have a stand where you can put your delivery tube into, and a measuring cylinder upside down. And the measuring cylinder is initially filled with completely with water, and when the gas is collected and escape up here, it will push, the bubbles will go all the way upwards and will displace or push the water downwards. All right, so the water level will gradually go down, and with that you can time your collection, time your reaction and collect the data and plot it into a table. And after that, after you've collected all your data on your table, you will plot into a graph. So here we have the y-axis, we have the volume of gas that's produced, and here on the x-axis we have time. So initially, when you plot it, you should kind of do a best fit curve, and initially it should be a lot of the rate of reaction is high, simply because there's a lot of reagents involved and a lot of collisions occurring, and with that a high amount of collisions, you'll have more chances of successful collisions based on the collision theory, okay? And so that's what will happen, and then it will gradually slow down, the rate of reaction will gradually slow down in the middle section of the graph, and then plateau to an even line because no more gas is produced because the number of reagents is completely used up. All right. These are the what they call units for this graph. Let's not be concerned about that. It's either milliliters, or in our case we use centimeter cube, cubic centimeters. And the other method of collecting or measuring rates of reaction is by mass loss. Okay, so what you have is that you put two reagents, put one reagent or two reagents in the flask, and then you put the flask on the weighing scale. And so when you pour it in, you record the mass of at the very beginning you record the mass of the flask plus its reagents. So, or you can tear the flask if you want to, and then you just put the reagents in there, and then you measure them. record initially, all right? So when the reaction is happening, one of them happens to be a gas, you need that to happen, because if they're both liquid or they're both solid, what's going to, or one solid and liquid, what's going to happen is that you will not see a mass loss unless there's unless one of the mass escapes. And this method, the amount of mass will be gas, so the gas will find its way out into the room. And what you notice after you plot your graph is that the amount of mass that's left, initially you have a lot of mass, and then after that you will go down rapidly because the rate of reaction is high, again being because there's lots of reagents, and then it will slow down as the number of reagents starts to diminish or reduce, and then it will plateau out. And so what you have here is just a mass of the reagents that's left in the flask. All right? And finally, the third final method is the precipitate method. I think, ooh, dear me, let me tighten this up. Okay, this method is basically what we'll do mostly in class. First, you have the reactions that's happening inside. You put one of the reagents in the flask, and then you will put the flask on top of a white piece of paper where you clearly label with a dark Sharpie or something with an X, and then you can see through your flask to the X that is labeled on your paper. And when you look at it, it will be like really clear. Then you put your other reagent in there and you start swirling the flask on top of the X spot. And while you swirl the flask, a reaction will occur, and you begin to see precipitation appearing from the reaction, and then you will see the X will start fading out, and then finally, when the reaction has completely done, or when you can't see the X spot, you will stop your timer. All right? Oh, don't forget you start the timer from the very beginning as well. And so this is more of a like qualitative observation with you only be able to time the reaction. And so because this is quite different, you can't really plot it this way. So what you have to do is that you have to take the 1 over time, the inverse time data. So you have to take the time that you measured and you put 1 over the time that you measured, and then you plot it based on the independent variable that has been asked, whether this is based on concentration or temperature or other things, okay? And then you plot it here, and then because it's 1 over time, your graph should look straight. So you have a best fit line here. All right? So these are 3 simple ways to measure the rate of reaction. So hopefully the video comes out great.